Imagine standing in the middle of a massive library, but, not just any library.
Right, a really big one.
Yeah, exactly. One that contains 1 billion books. And they aren't sorted by author, they're not sorted by genre, and there is absolutely no card catalog anywhere.
Which sounds like an absolute nightmare, honestly.
Totally. Now imagine someone hands you a title and says, go get this exact book. Oh, and by the way, you have a fraction of a microsecond to find it.
Yeah, impossible.
Right. In the physical world, sure.
Yeah.
But in the digital world, your devices do something exactly like this, millions of times a second. Welcome to the deep dive. Today, our mission is to explore the computer science wizardry that makes this instantaneous finding possible.
And it really is wizardry.
It is. We are talking about minimal perfect hash functions.
It's a form of digital magic, yeah. But magic built on incredibly rigorous mathematics and some really, really clever engineering tricks.
Absolutely. And to guide us through this, we're drawing on 2 main sources. First, a really heavy, comprehensive 2025 academic survey. It's called Modern Minimal Perfect Hashing, a survey by Lehman and colleagues.
It's a fantastic paper, really covers everything.
It does, and we're pairing that with a visual slide deck titled Mastering the Perfect Hash Trilemma. And look, whether you are querying a massive global database or, relying on real-time speech recognition on your phone or looking at DNA sequencing.
Bioinformatics, yeah.
Right. Bioinformatics. The invisible algorithms we're unpacking today, they dictate exactly how fast your digital world moves.
They form the unseen infrastructure of modern computing. Literally everything relies on them. And the constraints they operate under are just, they're punishing.
Punishing is a good word for it.
Yeah, so if we want to understand how they pull this off, we really have to look at the math behind the curtain.
Okay, let's unpack this a bit, because before we can understand what makes a hash function perfect, we should probably establish why standard hash functions are, imperfect.
Right. Standard hashing has some flaws.
So let's use an analogy. Standard hashing is essentially like people grabbing random seats in a massive movie theater.
That's a good way to put it.
You take your data, run it through an algorithm, and the algorithm just points to a seat. But eventually, 2 completely different people are going to try and sit in the exact same seat.
Exactly. And that right there, that is a collision.
A collision?
And that is the absolute nightmare scenario for software engineers. To deal with those collisions in standard hash tables, you usually have to make the theater much, much bigger than the actual number of people attending.
Ah, so you need more chairs than people.
Right. You create an array that's way larger than your set of keys. Plus, you have to build these really complex backup rules for when people bump into each other. You have to tell the computer, hey, if seat A is taken, walk 3 rows down and check seat B.
Which sounds exhausting.
It is. It takes up extra space in memory. And honestly, more importantly, it takes extra time.
But a minimal perfect hash function, which let's just call it an MPHF from here on out to save some breath, it's entirely different. It acts like a perfectly orchestrated VIP seating chart.
A very strict VIP list.
Exactly. So if you have exactly 1 million guests, you have exactly 1 million seats. The algorithm guarantees a completely collision-free mapping to those specific seats.
It's a perfect one-to-one relationship, or a bijection, mathematically speaking.
Right, a bijection. Everyone has exactly 1 seat, and there are 0 empty chairs left over.
But the crucial distinction here, though, is how it handles strangers.
Oh, right, because it's a VIP list.
Yeah, it only guarantees this perfect seating behavior for the known guests, the original input set. It completely ignores what happens if an uninvited guest shows up.
So what happens if I give it a random name?
If you feed it a key that wasn't on the original list, the function doesn't throw an error. It just points them to a random already occupied seat.
Wait, why doesn't it know they're not on the list?
Because it doesn't actually store the guest list.
Oh, wow. That's wild.
Precisely. It doesn't need to know they aren't on the list. By giving up the ability to recognize strangers, we don't have to store the actual data inside the index. And that is what enables this extreme space compression.
And when we say extreme, we really mean it. The sources point out there is an absolute mathematical limit to this compression. They literally call it the speed of light for perfect hashing.
Yeah, the theoretical lower bound.
And it is exactly 1.443 bits per key, meaning you only get basically 1.443 bits of digital ink per guest to write down the complex rules of your entire seating chart.
What's fascinating here is why that specific limit exists.
Nice.
Remember, you aren't compressing the data itself, right?
Right, the data isn't in there.
You are compressing the behavior of the function. The math relies on this concept called combinatorial entropy.
Okay, stop right there. Combinatorial entropy sounds like, I don't know, something from a quantum physics textbook. What does compressing behavior actually mean in plain English?
Fair enough. Think of it this way. Let's say there are billions of possible ways to arrange your guests in those seats. Since we know exactly who our specific guests are beforehand, we just need to tell the computer which specific seating arrangement to use.
Okay, I'm with you.
We are picking one single perfect blueprint out of a massive universe of possible blueprints. So the math, which uses these probability formulas to calculate the absolute minimum amount of information needed to distinguish our perfect blueprint from all the wrong ones, it basically bottoms out at roughly 1.443 bits per key.
Wow.
You simply cannot write the instructions using less information than that. It's mathematically impossible.
But here's the thing that gets me. If 1.443 bits is the absolute theoretical speed of light, why don't all algorithms just use that formula?
Because it's never that easy.
Right. Why do we have a massive 2025 survey detailing dozens of totally different approaches? Well, because in computer science, you can never have it all. Enter the engineering trilemma.
The trilemma is the absolute heart of the problem here. You have three competing axes. First is space consumption, how close you can get to that 1.443 bits limit.
Okay, space. Got it.
Second is construction time, meaning how many keys you can process per second to actually build the index in the first place.
Right.
And third is query time, how fast you can look up a key later on, which is usually measured by how many times the computer has to search its physical memory.
Okay, so space, construction time, and query time. The sources call modern MPHF engineering the art of strategic sacrifice. No single algorithm dominates all three dimensions.
You always have to give something up.
But I have to push back a little here on behalf of the listener. I look at my computer right now, and memory is incredibly cheap. I mean, I have terabytes of storage sitting right on my desk. Why are computer scientists fighting over fractions of a single bit? Who really cares if an algorithm uses 1.4 bits or like 3 bits per key?
It's a super valid question, but you have to scale up the problem to an industrial level. Think about bioinformatics, right? When researchers are sequencing DNA, they use these massive maps called De Bruijn graphs.
Right.
They chop the DNA into billions of tiny puzzle pieces called kamers. Or, think about massive global databases analyzing petabytes of consumer data. When you have tens of billions of keys, an extra bit or two per key suddenly balloons your index by gigabytes.
And gigabytes don't fit where you need them to fit.
Exactly. That is the physical bottleneck. Modern computer chips have this lightning-fast memory called L1 and L2 caches built directly onto the processor itself.
But they're pretty small, right?
Very small. They're measured in kilobytes or maybe a few megabytes. If your index is too big, it gets pushed out of that super-fast cache and down into the computer's main system RAM.
Oh, I see.
And accessing main RAM is excruciatingly slow from the processor's perspective. It's basically the difference between grabbing an open book right from your desk versus driving to a library in another city to take a single page.
Oh, wow. That puts it in perspective. So in this context, space actually is speed. A smaller file size means the index stays right on the desk. And that means vastly faster queries.
That's the exact problem. So to conquer this trilemma, engineers have developed completely different strategies based on which of those three axes they're willing to sacrifice.
The art of strategic sacrifice.
Exactly. The sources show researchers splitting into a few distinct camps.
Let's explore those camps, starting with the group that prioritizes highly predictable, guaranteed speed. How do they solve it?
They use a mechanism called retrieval. And the core of the retrieval approach is solving linear equations over hypergraphs.
Whoa. Solving linear equations over hypergraphs.
I know, it's a mouthful.
That sounds incredibly intimidating. Can we visualize this somehow? The sources mention a process of mapping, peeling, and orienting.
Let's break it down. Imagine your data keys as connections or wires linking different points together. A hypergraph is really just a complex web of these wires.
Okay, big web of wires.
The goal is to untangle the web so that every wire points to exactly one distinct location. The most crucial step is the peeling phase. You look through the web to find a point that only has one single wire connected to it.
Ah, so it's like untangling a massive ball of Christmas lights.
Yes.
You have this huge, chaotic knot of wires. You look for a bulb that is only connected to one loose wire. You pull it out, that's peeling. Then you find the next loose one, and you pull that. And you just keep pulling the loose ends until the whole knot falls apart perfectly.
That is a perfect visualization.
Yeah.
You peel away the easy connections, save their positions, and suddenly the complex connections underneath them loosen up. And the math behind this is just incredibly precise.
How so?
For certain types of these graphs, like 3 uniform hypergraphs, there is a sharp mathematical breaking point at exactly 0.8185.
0.8185.
Yep. If your ratio of wires to points is below that number, the knot will almost certainly untangle. If it's above it, it just stays a knotted mess forever.
That's wild that there's a specific number for that. And once it's untangled, you orient the graph, which basically means the computer stores exactly which configuration yielded that perfect seating chart for each guest.
Right, you lock it in.
And the flagship algorithms doing this today are really pushing the boundaries. You have SICK-hash, which achieved a massive leap by dynamically separating where it places keys from how it retrieves them.
It's very clever.
It gives harder to place keys more choices, hitting about 2.2 bits per key. And then there's Morphish hash. It trims down the connections into a pseudoforest, a highly streamlined structure to eliminate redundancies. And it hits an incredibly dense 1.489 bits per key.
Which is astonishing. And if we connect this to the bigger picture, the primary advantage of this entire retrieval approach isn't just the small space, it is the highly predictable query times.
Because it's just math.
Exactly, because untangling that graph requires a constant fixed number of mathematical operations. The computer knows exactly how long every single search will take.
No surprises.
Right. That predictability is vital for systems that need guaranteed response times, like internet routers directing network traffic, or massive server backends used by major tech companies. They need that stability.
So that gives us predictable speed. But what if that isn't your primary constraint? What if your absolute priority is making the index file as small as mathematically possible? How do you squeeze closer to that 1.443 bit speed of light limit?
That is when you bring out the hammer.
The hammer.
But a very smart, highly engineered hammer. We're talking about the brute force approach, specifically relying on recursive splitting and bucket placement.
Okay, the core insight from the sources on bucket placement is that you group your data into buckets, but you have to place the largest, most heavily populated buckets first into a mostly empty array.
Right, because it is fundamentally a packing problem. You put the big rocks in the jar first, then the pebbles, then the sand.
Makes sense.
If you try to fit a massive rock in at the very end when the jar is mostly full, it simply isn't going to fit. You get collisions everywhere.
And the flagship algorithms here are absolute monsters. You have FAST and PureHash. They are the undisputed kings of throughput. PureHash maps values to exactly 1 byte fixed with seeds. It is unbelievably fast.
Blazing fast.
But then on the other end of the brute force spectrum, you have Consensus RS. It uses fixed choices and complex backtracking algorithms across a splitting tree to hit 1.444 bits per key.
It's mind-blowing.
That is a mere 0.1% away from the mathematical limit.
It practically touches the speed of light. It's as close as you can get.
But here's where it gets really interesting, though. I gotta play the skeptic again. We're calling this brute force. Isn't brute force just a lazy programmer's way of rolling the dice millions of times until the computer gets lucky and finds a fit? How is that an elegant algorithm?
It's a common misconception, honestly.
Yeah.
But modern brute force is definitely not blind guessing. Think about the simple approach, trying random seating charts until you find a perfect one. The math shows that for any large number of guests, you would need to guess more times than there are atoms in the universe. It would take billions of years.
Which obviously doesn't work for a computer that needs to build this in seconds.
Right, which is why these modern techniques use recursive splitting. They don't try to guess the whole maze at once. They sort the data and mathematically chop the massive problem into microscopic chunks of just like 8 to 16 keys.
Oh, so they break it down.
Exactly. They mathematically shrink the universe of possibilities. A modern processor can easily brute force the right path for 8 keys in a nanosecond. It is highly structured, highly engineered probability.
So they are building a maze where all the dead ends are blocked off before the rat even starts running. That's brilliant.
Exactly.
Okay, so we have retrieval for predictable speed, and we have brute force for ultimate space compression. But what about the third point on our trilemma? Construction time.
Right, the build phase.
What if I need to build this index on the fly, in real time, over and over again?
Then you have to change your approach completely. You use the fingerprinting family.
Fingerpin.
The core mechanism here relies on layered, cascading bit vectors to resolve collisions. Essentially, you throw your data against a digital filter.
Wait, so it's like panning for gold?
Sort of, yeah.
Like you throw all the dirt over a wide, coarse grate, that's layer 1. Most of the dirt falls through, but some rocks hit the exact same holes and bounce off. Those are your collisions.
Right.
So the collisions fall onto a second, smaller grate below layer 2, and you keep cascading down through these layers until every specific piece of gold has its own distinct hole.
That is a very physical, intuitive way to understand it. You filter out the easy placements first and only deal with the collisions on the layers below. And the flagship algorithm using this method is called FIPS, which stands for Fingerprint Perfect Hashing via Sorting.
Okay, Fippius.
And what FIPS does is solve a massive hardware bottleneck that plagued older fingerprinting methods.
What kind of bottleneck?
Well, older methods required the computer's processor to constantly jump around its memory, checking those different grates.
Oh.
Even worse, when multiple processor cores tried to update the exact same spot on a grate at the exact same time, they created a traffic jam.
Oh, because they're all trying to use the same hole?
Yes. In computer science, this is called an atomic lock. It literally forces the entire system to stop and wait until the traffic clears.
And as we established earlier with the desk analogy, random memory jumps and waiting around are the absolute enemies of speed.
Which fundamentally changes the math. So FitPS bypasses this traffic jam entirely by simply sorting the fingerprints first.
Meaning, instead of checking the grate over and over, you arrange all the dirt by size first and then just dump it through the holes perfectly.
Exactly. By turning a chaotic, random collision problem into a neat, linear sorting problem, you trick the CPU into working at maximum efficiency.
That's so smart.
It eliminates the atomic locks entirely. It makes the algorithm incredibly cache-friendly
Yeah.
and allows it to scale linearly across dozens of processor cores simultaneously. It's just blazing fast to build.
Okay, so we have our three distinct camps: retrieval, brute force, and fingerprinting. But looking at the 2025 survey, it sounds like these aren't completely isolated camps anymore. Are engineers just, picking one and staying in their lane?
Not anymore, no. It is the natural evolution of the field. Computer scientists are now mating these algorithms together to create super
As
hybrids,
Frankenstein algorithms.
basically. You take the best mechanism from one family
Yeah.
and use it to mitigate the weakness of another.
The sources highlight a few of these. For example, shock hash. It uses the brute force recursive splitting to chop up the keys, but instead of brute forcing those final tiny chunks, it uses the retrieval math to untangle them.
Right, combining the two.
It gives you 1.489 bits per key, but vastly accelerates how fast you can query it. Or FMPHGO, which takes the fingerprinting cascades, the gold panning we talked about, but applies a localized brute force search to test multiple grates at once, drastically reducing the space overhead.
Which raises an important question for you, the listener. With all these hybrids and specialized tools, how do you actually choose the right one for your specific project?
Yes. Let's give them the ultimate cheat sheet based on the sources.
Let's do it.
If someone listening is building a massive system tomorrow, let's walk through the decision matrix.
Okay.
Let's say my primary constraint is that I need the absolute fastest queries possible. I am doing real-time internet packet inspection, and I cannot afford a single millisecond of delay.
Then you choose fast or PSHISH from the brute force family. Their use of fixed width chunks means the computer only ever has to check its main memory exactly one time per query. It is the gold standard for speed.
Okay, what if I'm strictly bound by memory size? Like I'm putting this code on a tiny embedded device, or I am scaling to trillions of keys for a global database, and I absolutely need the file size under 1.6 bits per key.
Then you pivot to consensus RS, or shock hash. Their advanced backtracking pushes memory consumption to within a fraction of a percent of the physical lower bound.
Got it. What if my data changes frequently? I need highly parallel real-time construction to rebuild the index across multiple processor cores every few minutes.
You choose FIPS or FMPH. Their cache line sorting completely bypasses those memory traffic jams we talked about.
And finally, what if I just want the best overall middle ground? I need a predictable balance of space and speed with no extreme latency penalties.
SICASH or PHAPIC. They sit beautifully right in the middle of the trilemma, giving you a very predictable 2.0 to 2.5 bits per key with great all-around performance.
So what does this all mean? We started by talking about the absolute speed of light limit of 1.443 bits. We explored how the trilemma of space, construction, and query time forces engineers to make strategic sacrifices.
Wait,
And we mapped out how untangling hypergraphs, shrinking brute force mazes, and cascading filters tackle those sacrifices in totally different ways.
It's a lot to take in. But there is one final detail in the source material that completely upends everything we have talked about today.
Oh.
Yeah, that 1.443 bits per key limit. that mathematical law of the universe.
Yeah.
It assumes the data you are processing is completely structurally random.
Wait. What if the data isn't random?
That's the million-dollar question. The survey briefly mentions a cutting-edge variant called monotone minimal perfect hash functions, or MMPHFs.
Okay.
These functions look at the data and exploit its natural intrinsic order. For instance, alphabetical order for text strings, or biological order in genome sequences.
Oh, wow.
By relying on the natural shape of the data itself, these functions smash right through that 1.443 speed of light limit. They can achieve index sizes that are mere fractions of a single bit per key.
Oh, wow. So as machine learning gets better and better at predicting data distributions, the algorithms of tomorrow might bypass this entire engineering trilemma.
Exactly.
They won't need to brute force a solution or peel a hypergraph. They will simply learn the exact shape of your data and map it perfectly based on its own internal logic.
It is a profound shift in how we think about computer science,
Yeah.
moving from structured randomness to learned deterministic order.
That is something to ponder next time you're staring at a loading screen. Thank you for joining us on this deep dive. Take a look at your own data pipelines this week. What are your constraints? What strategic sacrifices are you making without even realizing it?
It's always a trade off.
Because somewhere deep in the architecture of your favorite app, an invisible seating chart is being drawn up in fractions of a microsecond, making sure you find that one specific book in a billion exactly when you need it.